key feature of the Dold speed monitoring relays is that they're super easy to configure and use. Given 1 or 2 proximity sensors in, it can be set up to monitor overspeed, underspeed, speed inside a window, or speed outside a window. Let's set up one for overspeed monitoring. There are wiring diagrams for each case in the user manual. Here's how I wired my little demo station. First, I'm only using one NPN proximity sensor, so I just wired it to both inputs. Whether you need 1 or 2 sensors here will depend on your system's needs. Just know that you have the flexibility to do either with this speed monitoring relay. The voltage and grounds are tied together inside the unit, so we don't have to replicate that wiring here. The relay is controlling the contactors like this, and monitoring your aux contacts like this. We'll use the auto reset in this first example, so we don't need a push button here. The contactors are wired in series between the motor and the variable frequency drive, which I'm using to control the motor speed. Here's my little test setup with the part numbers I'm using in this demo. Notice that this proximity sensor only detects this single hole each rotation, so the speed monitor will see just a single pulse per revolution. Well, great. I'll apply power to the speed monitor and press a button to wake up the display. Press the right button and then the left button to change the parameters. Get through all the various self-test and display messages. The power LED flashes green to remind you that you're in parameter entry mode. If it flashes red, well, something's wrong with the parameters. We can change the parameters, the display language, do a factory reset, activate change tracking, and see the Dold contact info. We want to change the parameters, so I'll scroll back up to that and hit OK. What function do we want? Well, we want overspeed detection. What do we want our overspeed frequency limit to be? How about 10 revolutions per second? Now this is important. Since our sensor is only generating a single pulse each revolution, we just put a 10 here. But what if we were using this sensor that sees the 36 sprocket teeth pass every rotation? Well, since the speed monitor will see 36 pulses per revolution, and we want 10 revolutions per second, we would need a 360 here. That's important to understand. The speed monitor isn't really monitoring motor speed here, it's monitoring pulses per second. If you remember that, you'll be in good shape. We can change the hysteresis, various time delays, and alarm handling. Now, we didn't connect a manual reset button, so we'll go with the automatic alarm reset. Let's get back to the top level menu, and that's it. Hit this guy to exit the menu system. And acknowledge that we made these changes. Well, the power LED is solid, so we know we're not in parameter entry mode, and we see the K1, K2 LED is lit. That tells us the contactors are enabled right now. This is the error LED, and this one lights up when timing delays expire. This chart in the user manual explains all of these and what the various flashing patterns indicate. We see the current shaft speed is less than 0.75 Hz because the motor isn't spinning. If I turn the motor on, then we see the frequency of the pulses coming into the speed monitor, which in this example is just 1 pulse per revolution, so we are seeing the actual shaft speed. I'll increase the motor speed up past our 10 Hz cutoff and what's going on? My system is freaking out. We see the contactors are turning on and off over and over again. What's going on? Well, we increased the motor speed to exceed the cutoff, so the speed relay opened the contactors to kill power to the motor. And when the motor slows down enough, the speed monitoring relay automatically resets because we told it to, and it closes the contactors. The motor ramps back up past the frequency limit, so the speed relay cuts the motor off again, resets again, enables the motor again, etc. So we're stuck in this reset loop. If I slow the motor back down, then everything gets back to normal. So the issue is, the automatic reset is sending us right back into default mode. Let's turn the motor off while we fix this. Let's hold these 2 buttons down again to get back to the menu, work our way down to parameters, alarm memory, and switch to alarm memory, which requires a manual reset, and hit OK. I'll back out of here until I see the confirmation screen. It's reminding me I changed something, we know that, so I'll hit OK, and we're back to the main screen. I added a momentary push button like this. Now if I increase the motor speed, as soon as it hits 10 Hz, or really 10 sensor pulses per second, the speed relay opens the contactors and shuts the motor down, but this time without automatic reset, it stays there. I'll reduce the motor speed, then press reset, and the motor's back up and running. Exactly what we expect. The key thing to remember is the speed you see here isn't rotations per second. It's the number of pulses per second that the speed relay sees. Since we only had 1 pulse per revolution, it also happens to be the rotation rate in hertz. So the bottom line is, you're entering the frequency of the incoming pulses in hertz. I love how easy this is to set up, and that I can see at a glance exactly what configuration I have without having to decode a bunch of jumpers or dip switches. And since it uses digital NPN or PNP inputs, you don't have to spend a lot of time calibrating or tuning analog inputs. That saves you a lot of time and frustration and just makes your system more reliable and stable. And since there is no restriction on the current draw of the proximity sensor, you aren't limited to a proximity sensor. You could use a contrast sensor, an optical sensor, or pretty much anything you want that has a standard NPN or PNP output.